Hi everyone, we're going to finish off related rates today with just going over a couple more problems. So here is the first one. A Toyota Corolla is traveling west at 50 kilometers per hour and a Subaru Forester is going north at 60 kilometers per hour. Both are headed to an intersection of the roads. At what rate are they approaching each other when the Corolla is 0.3 kilometers and the Forester is 0.4 kilometers from the intersection? Okay, so as per usual with these types of problems, the first thing that we want to do here is draw a diagram. Oh, I'm in red. I'm going to switch to black. There we go. And I like to just draw out a little compass when I'm dealing with directions. There we go. So they're both heading towards the same intersection. So maybe I'll just put an I for the intersection. And the Corolla is traveling west. So the Corolla must start out somewhere over here. And the Corolla is going this way. And the Forester is heading north. So the Forester must start out below the intersection and it's going this way. And we want to know about the rate that they're sort of approaching each other, which is about how fast are they getting closer together. So we're interested in the rate of the distance between them, okay? So let's call that distance D. And I'm going to call the distance between the Corolla and the intersection C, and the distance between the Forester and the intersection F. And thankfully, this is a nice right triangle. So we have a relationship now between D, C, and F, and we have a Pythagorean relationship. Okay, so we know that D squared equals C squared plus F squared. Okay, so that's good. Now, what else do we know? We know that the Toyota Corolla is traveling west at 50 kilometers per hour. Now, that would be dc by dt. That is the Corolla's rate of change, okay? Here's kind of the tricky part though. The Corolla's distance is actually decreasing as it gets closer and closer to the intersection. So we're considering the distance between the Corolla and the intersection. So this rate of 50 should actually be negative 50, okay? And that's because, again, the distance between the Corolla and the intersection is decreasing because the Corolla is going towards the intersection, okay? We also know that the rate of the Forester is 60, but again, the Forester is getting closer to the intersection. So it's like it's narrowing in on the intersection, okay? The distance between them is decreasing. So this is also negative 60, okay? So this is what do we know? Okay, so this is sort of like the second step. What do we want to know? We want to know what is the rate that they're approaching each other. That's dd by dt. Specifically, when the distance between the Corolla and the intersection, that's C, is 0.3, and the distance between the Forester and the intersection, F, is 0.4. Okay, well, might be a good idea to actually just draw that out. So if I draw out a little picture, this is now 0.3, this is 0.4, and because I know two sides of the right triangle, I also know the distance between them because this is the square root of 0.3 squared plus 0.4 squared, which is, it happens to be 0.5. Okay, so I know those three things as well. I know C is 0.3, F is 0.4, and I had to do a little bit of work, but I could figure out that D is 0.5. Okay, now I'm ready to differentiate this guy with respect to time. So this is going to be step 3. And what I'm going to hope is that I'm going to know everything once I differentiate except for dd by dt, because that's what I want to find out. Okay, so let's try that and see what happens. So I'm going to go d by dt of d squared equals d by dt of c squared plus d by dt of f squared. Okay, and when I do that, we're doing implicit differentiation here, we're going to get 2d times dd by dt equals 2c times dc by dt, should be like a capital, there we go, plus 2f times df by dt. Okay, and let's see, we know d, that's 0.5. We don't know dt by dt, that's what we're trying to find out. We know that c is 0.3, dc by dt is -50, f is 0.4, and df by dt is -60. So we know everything but dd by dt. So we can plug everything in and solve for dd by dt. So now we're going to sub in what we know. Okay, so we know d, that's 0.5. We know c is 0.3, dc by dt is -50, plus 2 times f, 0.4, times df by dt is -60. Okay, and then 2 times 0.5 is 1, so that's dd by dt, 1 times dd by dt is just dd by dt, and then 2 times 0.3 is 0.6 times -50 is -30, plus 2 times 0.4 is 0.8, times 60 is, I think, 48, -48. So that is -78, okay? So what does this mean? It means that the distance between the two cars is decreasing at a rate of 78 kilometers per hour, okay? Or you could say the cars are approaching each other at a rate of 78 kilometers per hour. That's another way of putting it as well. Okay? All right, so that's the first one that we're going to look at. We're going to look at one more. Here's another one. Okay. A camper shines a flashlight on a cliff 20 meters away. A bear 1.5 meters tall runs towards the cliff at 2.7 meters per second. How fast is the bear's shadow decreasing when he's 12 meters from the wall? Okay, so we're definitely going to need to draw a diagram here. And in this diagram, here's our cliff, and here's the ground. Okay, and basically there's like a flashlight on the ground being shone towards the cliff. Okay, and then there's a bear. So maybe, I don't know, I'll draw the bear. I'm not very good at drawing. I'm just going to draw a stick man. We'll pretend that that's the bear. And so essentially the flashlight's being shone. The shadow is going to hit right there, right? So the cliff is going to keep going, but the shadow is going to hit right there. Okay, and this again, that's a nice right angle. And so we need to sort of draw in what we know here. Okay, so what we know is that the bear, that's this over here, oh, and that's also a nice right angle, that's good, is 1.5 meters tall. And we also know that the distance between the flashlight and the cliff is 20 meters. So this over here is 20, and this is 1.5. Okay? What we don't know is we don't know the shadow, and we don't know, the bear is sort of running away from the flashlight. So the distance between the flashlight and the bear keeps increasing. And in fact, it's increasing at a rate of 2.5 meters per second. So we don't know this. I'm gonna call this Y because it's sort of on the vertical. And we don't know this. This is X right here. Okay? Now if this section's X, this section over here has to be 20 minus X because they have to add up to 20. Okay, now you might think that we have to rely on Pythagoras here because we've got right triangles, but in fact we don't, because in this scenario we don't care about the hypotenuse. The hypotenuse doesn't come into this at all. What we care about is Y, the length of the shadow, and X, which is the distance of the bear from the flashlight. Okay, now what we are going to rely on here is something that we haven't come across yet, and that is the fact that these two triangles are similar to one another, okay? And that's because they both share this common angle down here, and they both have a right angle. And if two triangles rather have two angles that are the same, they have to have the third angle the same as well, because the third angle is going to be 180 minus the other two. Okay, so if the two triangles are similar, what that means is that their corresponding sides are proportional to one another. And so if we compare, let's say, the height to the base of the one triangle, it has to equal the height to the base of the other triangle. Okay, so the two triangles are similar. So if I compare, let's say I'm comparing the height to the base of the big triangle. Height is Y. The base is 20. That has to equal the height of the small triangle, which is 1.5, over the base of the small triangle, which is X. Okay, now I've got an equation that relates X and Y. Okay. Now, if I wanted to solve this for Y, I'd multiply both sides by 20, right? And 1.5 times 20 is 30, so that's going to give me Y equals 30 over X. So this is a really good start. Okay. Now, what do I know? So this is kind of part 2. I know that the distance that the bear is running away from the flashlight, which is X, is changing at a rate of 2.7 meters per second. That is dx by dt. So that has to equal 2.7. Okay, and it's increasing because he's running away from the flashlight. What I want to know is how fast is the bear's shadow decreasing? The bear's shadow is Y. So what's the rate that that's changing? The rate that that's changing is dy by dt when he's 12 meters from the wall. Well, now this is where this gets tricky because we've defined X to be the distance from the bear to the flashlight, okay? So if he's 12 meters from the wall, that means that 12 equals not X, but 20 minus X. Okay? Well, if we know that 12 equals 20 minus X, we can figure out X. Okay? So that means X has to equal 8. And as long as we know that, then we're good. Okay, so what we can do is we can take this equation over here and differentiate this with respect to time. Right, so that's going to be step 3. And then hopefully in step 2, we've sort of got enough to go on that we'll only have one unknown when we do step 3. Okay, so I'm going to rewrite this equation using a negative exponent. So instead of 30 over y, I'm going to write it as y equals 30 over x, I should say, as 30x to the negative 1, so that I can use the power rule there. So that if I take d by dt, rather, of y, and that's going to equal d by dt of 30x to the negative 1, I'm going to have to take the derivative there so I can use the power rule. Okay, so this is just going to be on the left dy by dt. And on the right, I'm going to have 30 times negative 1x to the negative 2 times dx by dt. Okay, and if I simplify that a little bit on the right, that gives me negative 1 times 30, negative 30 over x to the negative 2x squared times dx by dt. Okay, and I know what x is, and I know what dx by dt is, so I can now figure out what dy by dt is. Right, I can sub here. I know that x is 8, and I know that dx by dt, oh, sorry, I meant to sub that in. What am I doing? There we go, let's erase that. Dx by dt is 2.7. So I'll sub that in as well. Okay, and when you do that, you get, if you do that on a calculator, it's about negative 1.3. Okay, so what does that tell you? The rate of the change of the bear's shadow is negative 1.3, and I think it's meters per second. Yes, so the bear's shadow is decreasing at a rate of 1.3 meters per second, right? The negative sign implies that we are decreasing. Okay? All right, so that's it for today. I will hopefully see you guys soon.